You have a ball that starts at the top of this circular ramp of radius 4. It's falling down, and you want to know that the force that the ramp exerts at the ball when it falls to an angle of 60 degrees, and you have the mass of the ball as 60 kilograms. So you'd start out with a quick free body diagram of the ball here, falling down the ramp, and you have the ramp exerting a force on the ball of n sub s for normal at the surface. It's accelerating down, so you have an acceleration, the tangential acceleration here, because as it falls down, gravity is accelerating it at different rates, but it's accelerating. You have the acceleration, which is normal, directed inboard, and then finally you have the weight of the ball itself, which is the mass, 60 kilograms times 9.81. And it's good to denote in here the angle, this angle here is theta, is going to be 60 degrees as well. And we can know that real quick by looking at the diagram itself. This angle here is going to be 90 degrees. This angle is 60 degrees. So this will be 30 degrees. And if we take the portion of the ramp here where the ball is falling, we know that this whole angle is 90 degrees, so this area is going to be the 60 degrees we're looking at here. 90 minus 30 is 60 degrees. So go ahead and sum up our forces here. Sum of the forces in the normal direction equals, we got this force, this is considered positive. Normal at the surface, that force, and then you're going to have this force times the sine of 60. That'll be the component directed this way. So that'll be negative 9.81 times 60, 588.6 times the sine of 60 degrees. And that's going to equal the mass, 60 kilograms, times acceleration in the normal direction. And we know from physics that acceleration in the normal direction is in fact the velocity squared divided by the radius, which is 4. And we're going to use this equation later to solve for n sub s. So we can rewrite this real quick. N sub s equals 588.6 sine of 60 degrees equals plus 60 times v squared over 4. And once we find v, we'll be able to sub it in here and solve for n sub s. Secondly, we get the sum of the forces in the tangential direction. Looking at our diagram here, we're going to have cosine of 60. That's this force directed this direction in the tangential direction. We're not going to multiply it out because it's a little bit easier, times 9.81 times cosine, and then keep this as theta, because as we'll see, we're going to integrate along theta, and we need to keep theta as a variable if we're going to do that. That's the only force in the tangential direction, and that's going to equal mass times acceleration in the tangential direction. And you see 60s just cancel out. So acceleration tangential is going to equal 9.81 cosine of theta. Now to find the actual velocity, we're going to use this identity dv over ds. So the change in velocity over the change in distance is equivalent to saying acceleration or velocity. dv is acceleration, ds is velocity. We can manipulate this algebraically to read v ds equals a, or v dv rather, equals a ds. You just cross multiply the terms here. Now ds isn't very useful to us here because we're not going to be integrating along a certain distance. We're going to be integrating along theta, since we know the initial value of theta is 0 and the final value of theta is 60. So we can use an identity here. We know that ds equals r times d theta. So if you move, say, from 0 to pi here, you're in fact going to move a distance of pi d theta times r, 4. So you're going to move a distance of 4 pi. Just this little identity here. So we're able to cross out d theta and sub it in and replace it with r d theta right here. And that's set up for integration. So we integrate from 0 to v final of v dv, and that's going to be equal to the integral of 0 to 60 degrees of acceleration in the tangential component times radius d theta. And I'm going to go ahead and rewrite this whole expression actually, because we know acceleration of the tangential direction is 9.81 times radius times cosine of theta. And so moving over here, 1/2 v final squared equals the integral of the cosine is the sine, so you're going to have 9.81 times 4, 39.24 times the sine of theta, integrated from 60 degrees is going to be the final limit, and 0 degrees is going to be the initial. And this is pretty easy to do. You just solve algebraically. You're going to get v final equals v final squared equals 78.48. Sine of 60 is going to be, we'll just keep it as sine of 60. And then this is going to be, of course, this lower limit, sine of 0 is 0, so you don't even have to worry about it. So you're going to get v final equals the square root of this number to the 0.5, 8.244, and that's your final velocity. You can take this final velocity and plug it in to this equation, 8.244 squared, and you're able to solve for, oops, I should have plugged it in down here, but you get the idea. N sub s equals 588.6 times the sine of 60 degrees plus 60 times v squared, which is 8.244 squared, and then you divide that by 4, and you are going to get a total normal force at this point of 1,529 newtons. And that's just the acceleration added up with the weight itself. And that's pretty much how you do it. Thanks for watching.